everyone. Welcome back to Learning at 11th Hour. Today, we are going to look at another very powerful technique which can be used to analyze circuits. It's called the node voltage method or the nodal analysis. So, let's look at how we are supposed to approach a problem using the node voltage method. So, in this, basically, we are going to analyze the voltages at every node in the circuit in order to compute the currents flowing through the different branches of the circuit. So, how do we begin? As already said, we need to first identify the nodes of the circuit. So, over here, we can see that there are actually 5 nodes as already marked over here. So the first node here is the one that is marked as 1. The second one is marked as 2 over here. The third one is the reference node. The fourth one is the node between the voltage source and 1. And the fifth one is the node between node 2 and the second voltage source VB. Before we go into the steps of resolving the circuit using node voltage method, let us consider this simple branch between the terminals or nodes X and Y. Say the voltage at node X is Vx and the voltage at node Y is Vy. And the resistance of this branch is R and the current is coming out of node X whose value is I. So we can write I to be equal to minus of Vx minus Vy. That is the voltage drop across the two terminals divided by R. And why the minus sign? That's because the current is coming out of this node voltage. So using this concept, we can incorporate the different values of the node voltages in this node voltage method. So let's get back to the steps that are involved in implementing the node voltage method. So the first step is to identify the nodes. Here, 5 nodes have been identified. The second step is to consider that at every node, the currents are coming out of the node into the various branches connected to it. So if this in node 1, there are 3 currents coming out. In node 2, again 3. Node 3 is the reference node, so all the currents are going to culminate over here. And at node 4, so we are basically going to find out the node voltages. So at node 4, the node voltage is nothing but VA. And at node 5, the node voltage is nothing but VB. Assuming that the node voltage of this third node is the reference node. So node voltage at the third node is going to be 0 volts. Now, having marked the direction of the currents, we now mark the node voltages. So this is V1 at node 1. This is V2 at node 2. These are the two node voltages apart from V4 and V5, which we already know are VA and VB. Now we can write the expression for these currents which we have marked to be coming out of each of these nodes. So let's begin by writing the KCL equation at node N1. So at node 1, the first current that is coming out is into RA from the first node. So I'm going to write it as minus of V1 minus VA by RA. Similarly, we can write the current going into RB as minus V1 RB and going into RC as minus V1 minus V2 by RC. All this put together is equal to 0 as per the Kirchhoff's current law. Now applying the KCL at node N2, what do we get? So the current that is going into RC out of the second node. So we can write it as V2 minus V1 by RC minus sign because it's coming out. Again, minus of V2 by RT and minus of V2 minus VB by RE. All this put together is equal to 0. So this way we have got two KCL equations, one for node 1 and the other for node N2. on simplifying these two KCL equations which we just framed, so the simplification of the first KCL equation gives us minus of V1 into 1 by RA plus 1 by RB plus 1 by RC plus 1 by RC into V2 is equal to minus VA by RA. So this is the simplified version of the first KCL equation, where we've taken the coefficients of the two node voltages together and made it look simpler. Again, we apply the same approach for the second KCL equation and we get V1 by RC minus V2 1 by RC plus 1 by RD plus 1 by RE is equal to minus VB by RE. So this becomes the second KCL equation. So if we look at this, we can actually look at two unknown voltages, uh, namely V1 and V2. So these are the two unknown voltages. And here we have a matrix which consists of the reciprocal of some resistances and 1 by RC. And here I have this entire thing 1 by, so let me call this as RX and RY. So I'm taking all of this. So I'm calling this entire thing in this bracket as RX, and this one is 1 by RX rather, and 1 by RY. So what I am getting is I'm getting the reciprocal of resistance, which is nothing but conductance, and I'm going to replace it with this variable G. And here I have V. So, of course, V by R is going to be nothing but I. And in this case, this current I is in the form of, again, as from the equation we can see, minus VA by RA and minus VB by RE. So, we can actually obtain the matrix in this manner, and we can apply Cramer's rule to find out the values of V1 and V2, the two node voltages. Once that is done, we can simplify this circuit and also compute the various values of the branch currents in this circuit. Now, that was a very general expression, and that only explained the approach towards the node voltage method. Let's look at an example over here. We need to compute the values of I1, I2, and I3 over here. So, they have simplified it for us in the sense that they've already marked the direction of the current and they are all coming out of the node, and there is just one node over here. So we need to compute this node voltage V1, which is the unknown, using which we can compute I1, I2, and I3 easily. They have said that this node is the reference, so that means this voltage is going to be equal to 0. So applying KCL at this particular node, we can say minus of V1 minus 20 by 5 minus of V1 by 10 and minus of V1 minus 8 by 2 put together is equal to 0. This is by applying KCL at node N1. So on simplifying, there's just one equation with one unknown. So we'll directly get the value of V1. So how do we do that? So we have I'll take the LCM as 10. So I'll get minus 2V1 minus 40 minus V1 minus 5V1 plus 40 is equal to 0. So this is basically going to be equal to minus 2V1 minus V1 minus 5V1 is equal to minus 80. So on simplifying, we get 8V1 is equal to 80. Therefore, V1 is equal to 10 volts. So if we know that V1 is 10 volts, what is I1 going to be? I1 is nothing but minus of V1 minus 20 by 5, which is nothing but minus of 10 minus 20, which is minus 10 by 5 amps, which is, again, you can cancel out the two minus signs and we get 2 amps. So in that manner, we can also compute the value of I3 as minus of V1 by 10. So that is uh, value of I3 is equal to minus of 10 by 10 amps, which is nothing but 1 amp. And the value of I2 can be obtained as I2 is equal to 10 minus 8 by 2, which is again equal to 2 by 2 or 1 amp. So in this manner, we can frame the KCL equation using the node voltage and obtain the node voltage from the equation by resolving the equation, and from that compute the branch currents. So that's all with this video on node voltage method. I hope the video was useful to you. In the upcoming video, we'll take up some complex problems using node voltage method, which would also include the dependent sources. Thanks for watching. Please do subscribe to my channel.